Alright, so let's begin section 19.2. This section is going to be about electromagnets and magnetic domains. Now, first of all, anytime you have current going through a wire, it creates a magnetic field. Okay? Anytime you have current going through a wire, there will be a magnetic field around the wire. So, just to kind of give you an example, what I've got here, I've got a compass, a paper clip. Now the paper clip has a little bit of magnetism left over from a demo I did earlier, but let's see. Darn. Ooh, I know. I've got a bit of copper wire here somewhere. Alright, I've got a bit of copper wire I'll use. Now, if I were to, I'm only going to briefly touch this because there's not a whole lot of resistance in this wire and I don't want to spark it. But if I were to apply a current to this wire, well, I think my battery might be dead. Darn. Wait, no. Here we go. There we go. We're not getting a very large reaction, but we are getting a reaction out of the compass. So you can see that there is a magnetic field created. Keep in mind, copper is not magnetic. So the only way that we could have had a magnetic field is because of the current. So, now the magnetic field that is created forms concentric circles about the wire. So if you had like a wire maybe through a sheet of cardboard or something with some iron filings sprinkled on top, you'll find that when you run current through it, the iron filings actually form circles around the wire. Now the stronger the current that you run through there, the stronger your magnetic field will be. But as you get further away from the wire, the weaker the magnetic field becomes. So lots of current, you get a strong field. But at the same time, if you get too far away, it's not going to be very strong. So, got to kind of make a balance there. Now, if I were to take that copper wire that I just showed you and make a loop out of it, I would actually be strengthening the magnetic field created inside of it. Because what happens is, let's say we make a loop out of the wire and we have current going through and it comes out on the other end. It would actually create a magnetic field around it. Okay. And with the way I've got mine drawn here, it ends up going upward. And when you add a bunch of loops in there, not just one, you form a coil which is called a solenoid. So that copper wire I had earlier, I wrapped it around an iron nail a few times and now I have a coil of wire which is called a solenoid. Now the more loops you add to your coil, the stronger your magnetic field is going to become. So the solenoid can produce strong magnetic fields by combining several loops together. So if I were to add even more loops to this and then run current through it, it would become an even stronger electromagnet. Because that's what it is. If you hook the coil up to a circuit, a source of voltage of some kind, you're actually creating an electromagnet. Now a solenoid acts as a magnet when it carries a current. So right here, what I'm talking about are electromagnets. Now there are different ways you can increase the strength of an electromagnet. You can increase the electric or magnetic field if you increase the number of loops or increase the current. You can also strengthen it by inserting an iron rod through the center of it. Now it says this is what creates the electromagnet, but actually it's really once you run a current through the wire. So let's take this here, and again remember that copper by itself is not magnetic. So I'm going to hook it up to a 6-volt battery I've got, and when I touch it you can see that there is a reaction. Not a very strong one, but there is a reaction. Now if I can find my iron nail, there it is. Keep in mind there's a little bit of residual magnetism, but you can also tell that we get a much stronger reaction. In fact, I am reversing the magnetic field that was originally in there. So by creating a current through there, I am creating a stronger magnetic field. Now, one neat thing about this, if I were to switch this around, I actually change what kind of magnetic field is created. So one more time, I'm going to put this one over here, and the way I had it just set up, it attracted, now it's going to repel. So the direction of your current can change what kind of magnetic field is created. But the thing is, my electromagnet that I just created is not really that strong. Okay, so if I have some paper clips here and I go to try to pick up some paper clips, it might work a little bit, but nothing's really happening. That's when I like to show this one. It's a very, very large iron spike with a lot of coils. Now this one's a lot more dangerous. If you make an electromagnet, one thing you have to be aware of is that there is very little resistance, which means that your wires can overheat or even spark. I don't know if y'all can tell, but I am getting a couple of small sparks here. That being said, I am going to get a much stronger magnetic field. Now I'm not running a current through there, so you can see there's a little bit of residual magnetism, but it's not very strong. It's not picking up a whole lot of them. But if I run a current through there, I'm able to pick up a bunch. Okay. So let's go on to the next slide. Now, moving charges, specifically electrons, let me actually write electrons, are what create magnetic fields. Electrons in the atom spin, and usually they tend to pair up with electrons that are spinning the opposite direction, so they cancel each other out. But some materials have unpaired electrons, which means not all of the magnetic field is canceled out. This is what happens in materials that are called ferromagnetic. Ferromagnetic has a very strong reaction to magnetic fields, so there's a lot of unpaired electrons. Now, within materials, whether they're magnetized or unmagnetized, there are large groups of atoms called domains, where all the atoms have magnetic fields going in the same direction. Okay? And in an unmagnetized substance, those domains are randomly oriented. Okay? So let me show you an example. I've got just drawing an example. If I have a material in different these sections are going to be my domains. In an unmagnetized substance, the domains in these areas will kind of go in all kinds of different directions. But if it is magnetized, again, draw it out here. If it's magnetized, all your domains will have magnetic fields going in the same direction. Now you can actually cause something to become magnetized, like I showed you with the paperclip earlier. When that happens, you are applying an external magnetic field to the object. And when you do so, what you're doing is you're causing the domains to go from this to this. You're aligning them. Now we mentioned hard and soft magnetic material earlier in section 1. In a hard magnetic material, this is one that's difficult to magnetize, but once it is, it stays that way. In a hard magnetic material, if you apply a magnetic field to the object and then remove it, the domains will stay aligned, which is going to create a permanent magnet. But in a soft magnetic material, the domains return to normal once you remove the magnetic field. So let me give you an example. I've got a rock here. This rock is magnetic, okay? Probably has some iron in it or something like that. Now, the rock by itself is not going to pick up any paper clips, okay? It's not going to work. But if I apply an external magnetic field to it, the domains in this rock become aligned, and then it'll pick up paper clips. I'll try to show that it's just the rock picking it up and not the magnet. There we go. Well, not quite. But the rock is now magnetized because the rock is what's picking up the paper clips. You aren't getting a very good view of this, are y'all? Oh well. But again, without the magnetic field, it does nothing. But if you do apply a magnetic field, it'll pick it up. There we go. And as soon as I remove it, the domains go back to normal and it's unmagnetized. So again, nothing happens. Apply a field, it becomes magnetized. It's picking it up. But when I remove the field, the domains return to normal, and now they're random again. Okay. Where'd my pen go? There it is. Alright, so that's it for today's video, and we'll do section 19.3 next time.